Before we start with the talks of our partners, I would like to give you an overview of what is going on in the research area of batteries and fuel cells within GeoDict. As I already told you, my name is Ilona Glatt, and I lead the batteries and fuel cells team at Math2Market since 2016 now. I'm a trained physicist and I did my studies at the Technical University of Darmstadt and at the University of Mainz. And 1 year I spent abroad in Spain. Which systems are we dealing with in the battery and fuel cells area? Well, of course, this is first of all a battery. So here you can see a schematic of a lithium-ion battery. And how does it work in principle? Well, we have the lithium inside of the cathode active material, and when the battery is being charged, the lithium enters the electrolyte. It goes through the separator to the anode side, while the electron moves through the active material on the cathode side or the carbon black and binder domain to the current collector on the cathode side, and then it goes around the battery cell through the charger to the anode side, and together with its lithium ion, the electron enters into the active material on the anode side. Most often this is graphite. So this working principle already gives you a hint that the transportation and the pathways for the transportation is a key, a cornerstone in battery material design. If the transportation works well, then the battery is charged very easily and the performance is good. And what are the challenges that we are facing in battery material design in general? Well, first of all, our battery has to have a high energy density. It should be fast charging, and it should also be resistant to mechanical stress and aging. And what does that, on the other side, mean for the material design on the microstructural level, so for things that you can achieve with GeoDict? Well, with GeoDict, you can calculate properties like porosity, like tortuosity, diffusivity, and so forth. And these properties directly represent the transportation properties of the lithium ions and the electrons. And so these are key parameters that you can calculate using GeoDict. And these properties also determine directly the performance of the battery cell on a larger level, on a higher scale. So you can use GeoDict to design your battery material to be well performing on higher or larger scales. The other system we are dealing with in the battery and fuel cells area is of course a fuel cell, or to be more precise, a PEM fuel cell, a proton exchange membrane fuel cell. What is the working principle of a PEM fuel cell? Well, it generates electricity by oxidizing the hydrogen in a catalytic layer. The protons diffuse through the proton exchange layer, while the electrons drive the electronic circuit. On the cathode side, hydrogen and oxygen react to water here. As you can see, the PEM fuel cell setup consists of several individual layers with a unique microstructure and functionality. The challenges just for the material design here are the gas permeability and the water management, and the thermal and electrical conductivity. Usually the fuel cell operates at elevated temperatures, which is also stressful for the material. And in general, the mechanical stress and also aging is an issue here, similar as for the battery materials. As for the battery, here we can address and determine the microstructural properties of the materials in order to get effective properties for larger scales, also for larger simulations, larger scale simulations. Again, the microstructure is the cornerstone for the performance of the entire system. Which are the most important steps we need to take to tackle transport properties on the microscale? like the tortuosity, the porosity, diffusivity, and so on, which do determine the performance on the larger scale in the end? Well, first I would like to show you the creation of an artificially created representation of the microstructure of a real battery or fuel cell material, a so-called statistical digital twin. Second, we are going to address transport phenomena in the microscale of batteries and fuel cells. As already mentioned, these are directly represented by the porosity, the tortuosity, and so forth. In contrast to the fuel cells area, for the batteries, we are in the lucky position to directly test the performance of the material on the microscale during operation. This is done via quantitative charging simulations of the battery material. Now in GeoDict 2022, you can really start addressing battery aging on the microscale. And last, but certainly not least, I would like to point you to some insightful training materials which help you becoming an expert in using GeoDict. Let's start with the creation of realistic statistical digital twins. You can create statistical digital twins for the microstructure of each of the layers in a PEM fuel cell. Here you can see an example showing artificially created GDLs, MPLs, catalyst layer, and also the membrane. You already might have guessed that the layers are not to scale, but nevertheless I think it gives you an idea how these microstructures would look like. Similarly, you can create digital twins for each layer of a battery. Here, this was exemplarily done for a graphite anode and an NMC cathode. How do you get to such a statistical digital representation of your real material? Let's look at this process at the example of a graphite anode material. On the left-hand side, you see the original material. It was scanned, image filtered, segmented, and finally imported into GeoDict. On the right-hand side, you see the artificially recreated material, the statistical digital twin. The crucial point for a statistical digital twin is that the resulting transport properties like diffusivity, tortuosity, porosity, and so forth do match those of the original material. How do you get there? Well, usually you start with an imported scan of the original material. Very often it is not possible to distinguish the gray values of the active material and of the binder or of the carbon black and binder phase. What can you do in those cases? Well, you can identify the binder using the automatic binder recognition done by AI in GeoDict. You can either use the neural networks that are already predefined in GeoDict, or if those do not match your structure, you can also train your own neural network. Once the binder is identified, you can now start worrying about the rest of your structure, the active material or the grains. If you want to create the grains for a statistical digital twin, it is of course important to know the statistics of the original grains. You need to know the grain size distribution, the shape of the grains, the orientation, and so forth. To get this statistic, you can use grain find in GeoDict, which identifies each grain as an object and runs several statistics over all of these grains. Using these statistics as an input for the creation of the microstructure, you get a good representation of your original material. This works extremely well if your particles have ellipsoid shapes. Of course, if you have binder in your original material, you can also add that binder after the creation of the grains to the material. Using this representation as a basis, you can now start doing some post-processing on the structure to further improve the matching between the original material and the twin. For a fibrous material, like for example for this GDL we have here, the creation of a statistical digital twin works exactly the same way as it is for the granular material we had before. You start with an imported scan, you automatically identify the binder, you automatically run a statistic of your fibers, you use that statistic to create a fibrous material. In the end, you add the right amount of binder to your artificial material, and you end up with a statistical digital twin. Once you have a statistical digital twin of your material, you can start altering the structure to improve on the design of the microstructure. Here you can see an example from the Structure E project where we created a statistical digital twin of an anode material and then tested further designs of the microstructure. In GeoDict, you have another completely different method for the creation of a statistical digital twin, which is using the Gaussian random field method. I'm not going to delve into that, but instead I would like to point you to the following talk given by Philip Marmot of the ZHAW Winter Tour. Here, let us now focus on the transport phenomena which exist in batteries and fuel cells. What you can see here is a nice example for the importance of the identification of binder in a fibrous material like a GDL, for example. What was done? Well, we ran a simulation of the electrical conductivity on a GDL, and it turned out that the resulting effective conductivity did not fit to the experiments. So what happened? Was the experiment wrong? Or is something wrong with the algorithm? No. Of course, you have already guessed it. What happens is, if you cannot differentiate between the binder and the fiber, it is impossible to assign different conductivity values for each of the materials. And this is necessary to achieve correct conductivity. So if you identify the binder before calculating the conductivity of the structure, you can assign different values for the conductivity for the fiber and the binder, and then the conductivity, the effective conductivity in the end turns out to be correct and fit to the experiments. Similarly, in battery anodes, the anisotropy of the diffusion coefficient of graphite must be considered for a correct simulation of the effective diffusivity of the entire structure. On the left-hand side, you see the simulation of the diffusivity with an isotropic diffusivity value. But, especially for graphite, lithium ions may move much more easily in parallel to the main axis of the graphite particles than perpendicular to it. If you take this into account, as was done on the right-hand side, you end up with the correct effective diffusivity and also with a correct local diffusion flux field. This is a completely different story, but it also has to do with transportation effects. Here, the behavior of a standard GDL during water saturation was compared to the behavior of an improved GDL. For the improved GDL, the original statistical digital twin was pinched digitally with some holes. And when now water is being produced, starting at the bottom of the GDL, you can see that for the perforated case, the water moves through the pinched holes to the top, thus leaving the tiny pores between the fibers for the gas transport. This is not the case for the default GDL, and you can see that behavior also reflected in the graph on the right-hand side here, where in the perforated case, the water saturation is already much higher when the pressure for the gas transport is still lower than in the default case. In general, it is always important to compare the simulations to experimental results. Here, this was also done with experiments of the Saarland University, who kindly shared their results with us. More information on this experiment with wetting, neutral and non-wetting fibers is shown by Sven Linden in the Digital Rock Physics session. Concluding, you can say that you can address all the most important transport phenomena in a PEM fuel cell, starting from the water production in the GDL and the saturation of the GDL, over the flow flowing through the gas channel, and also the influence of the water saturation on that flow, resulting in reduced permeability of the structure. Now let's go back to the batteries and have a look at charging simulations of battery materials on the microscale. This is a battery structure consisting of an anode current collector, a graphite anode, a separator, an NMC cathode, and a cathode current collector. We use GeoDict to charge this structure. The colors indicate the local lithium concentration within the materials. You can see the overall concentration in the cathode side going down during the charging process, whereas on the anode side the concentration goes up. You can also see local variations of the concentration, which usually is not a good sign for the performance and durability of the material. We are often asked, how long does such a battery simulation take? The answer depends on a lot of parameters, not only the structure size, but also the particle size, the porosity, the number of materials, and so forth. But to give you a good estimate, we ran some benchmarking charging simulations for different structure sizes, ranging from 256 cubed to 1000 times 1000 times 256 voxels. We compared the runtimes in GeoDict 2020 and GeoDict 2021. The most important outcome, the results remained the same. But also, the simulation in GeoDict 2021 was 85% faster for the second largest structure. But maybe even more important is the required memory is reduced by over 90% by applying the Lear solver in GeoDict 2021. Only this fact allowed us to simulate the charging of the largest structure at all. This was not possible before with the GeoDict 2020 version. Until a few days ago, until the release of the new GeoDict 2022 version, the best solver in GeoDict had one tremendous advantage over the Lear solver. The best solver was able to account for the binder phase to be porous. Now, in the new GeoDict 2022 version, the Lear solver also allows you to input the porosity and tortuosity as effective parameters for the carbon black and binder phase. The simulation results are still the same as with the best solver in GeoDict 2021, but with the Lear solver the simulation is almost 40 times more memory efficient and also about 5 times faster. That means you can actually run such a charging simulation as shown here with porous binder on a 500 cubed structure in about 10 hours. For what we are going to do now, this speed improvement is crucial. We want to have a look on battery aging, for which a repeated charging and discharging of the battery material is a precondition. For battery aging, many degradation mechanisms play an important role. In our ongoing publicly funded projects, we so far focus on the mechanical degradation of the active material. As already said, Repeated charging and discharging of the battery material is a precondition to look at battery aging. This is why the new GeoDict add-on to BatteryDict now allows for a cycling protocol. This protocol can be adapted to your specific use cases. You can specify, for example, the type of charging or discharging, like constant current or charge rate, and also specify a stopping criterion when this charging or discharging step should be stopped by GeoDict and GeoDict can move to the next step. This way you can run entire cycling protocols in BatteryDict. In the Solve project, we had the unique opportunity to compare our simulation results with experimental results of the ETH in Zurich. We looked at the swelling of the active material during lithium intercalation. The ETH in Zurich did electrochemical in situ measurements of the charging of active material, while at the same time they took time-resolved, high-resolution micro-CT scans of the same material. These measurements allowed us to compare the swelling of the active material throughout the entire state of charge range. Here, on the left-hand side, we started with a scan of a pristine graphite anode, and on that scan, we simulated the swelling of the structure due to the changing lithium ion concentration. The colors also indicate the von Mises stresses which result during the intercalation of lithium ions. On the right-hand side, you can see the same material, but the expansion is shown via the corresponding in situ scan that was taken by the ETH in Zurich. This kind of comparison is very valuable for us, as it allows us to validate the simulations we newly implemented for the GeoDict module. The innovations I've shown you were made much easier by two publicly funded projects that we were part of, the Solve project and the Structure E project. And this is why I want to thank all our partners and also, of course, the funders. So far, we focused on the mechanical degradation mechanisms, but in the upcoming GeoDict versions, we are planning to include also SEI formation and lithium plating in the GeoDict module. At the end of this presentation, I would like to point you to some training materials which might help you in getting an expert in GeoDict. First of all, we have the tutorials, as PDFs or videos, as you prefer. Just have a look on our website and also on our YouTube channel. We have a wide range from digital battery material design through digital analysis of fibers and binder content of a GDL until image processing and image analysis. Also some Python, which might help you in getting automated scripts using GeoDict. Quite recently, we launched our forum, where you can start discussions with other GeoDict users, or you can just post questions which are then answered by our support or by other GeoDict users. Have a look. With that, I would like to thank you for your attention and point you to the next talks in this session. If you have any questions, I'm happy to answer those either now in the chat or via microphone, or you can also contact me later.